Greetings, everybody. My name is Mario Valladares. I'm a master's degree student from the Universidade Federal de Itajuba, Brazil. Today, I'm presenting the results of our investigation, the comparative analysis of voltage stability indices on the renewable injections in the IEEE 57 bus system. A paper developed by myself, Professor Lian Valenza de Lorenzi, and Professor Antonio Zambroni de Souza, both professors at the Institute of Electrical System Energy at UNIFE. Our route to present our analysis will be focused on the following key points: the challenge of renewable and grid voltage stability, just providing a quick insight of the challenges and difficulties of the modern power system, the concept of framework, the voltage stability indices, the VSIs, a brief explanation of what they are and a specific VSI used for this work, the methodology, the system model and simulations, the results, the base case and renewable injection case, a comparison between the cases and interesting points to analyze, and the conclusion and future work for this paper. Okay, our first key point for our route is the voltage stability challenges. Let's talk about the downsides of clean energy transition. Biorenewables like solar and wind are fantastic. Their power isn't constant, is variable and intermittent. This creates a roller coaster of power flow that can make a grid operate in unexpected ways, sometimes dangerously close to a breaking point that we usually know as the voltage collapse. So we need smarter, more advanced tools to predict this risk, because our old ways of measuring voltage stability are encoding for today's complex power system. For measuring these new behaviors in our power system and provide better planning and observability, we use what we know as voltage stability indices. Continuing our route, we have what voltage stability indices are. They are metrics used to analyze the proximity of electrical power system to voltage collapse, identifying critical buses or evaluating the robustness of a particular bus or system area. These methods are applied according to the specific aspect being assessed. In this work, three VSIs are employed: the tangent vector, the energy function based on power flow equation, and the reactive power margin, most commonly known as RPM. First of the VSI that we're going to be working right now is the tangent vector. It's a mathematical technique used as a predictor step in the continuation method to determine the system equilibrium point. The power flow equations are computer-based, and at some specific particular equilibrium point is defined as the following equation that we have over here, where the initial power flow data are used, the active and reactive power flow data, and the Jacobian matrix as well. Here we have this example of how the tangent vector works. We calculate the tangent vector using this displacement, a displacement of a parameter lambda. I'm going to mention later on a parameter lambda, until we get to the critical point. Further from there, we have our instability region. Basically, the tangent vector shows the system variables. In this case, we have the angle and voltage of our system change in respect of a variation of a parameter, as stated before. This parameter is here in our graph. It can be basically an increasing and decreasing of a load, for example. It defines the criticality of our system and provides the critical bus as well for our system in a quicker way, and allows the system to determine the critical area of itself in association of a cluster form of the TV ranking, the tangent vector ranking, in an analysis that is called the partitioning parameter, Cij. Later on, I'm going to be showing this parameter. The second of the VSIs is the energy function. Basically, it defines the difference of a potential energy between an operable power flow solution, that is usually the stable solution of our system, and the low voltage power flow solution, LVS, commonly known as the unstable solution part of our system. This value usually is a negative scalar value, and it usually is used to measure the robustness of a bus. Each possible LVS can be calculated, but not all LVS can be obtainable. Usually this is affected by the operative system, the iterative method that we use. It can be affected by a lot of things, so we can calculate this LVS. Usually a higher energy function value indicates a greater robustness against instability. And here we have our equation. The energy function that it depends on the stable and unstable part is usually the negative value of the difference of the unstable potential energy value and the stable potential energy value. Last of the PSI that we use in this work is a reactive power margin RPM that it derives from the QB curve. It provides a local reactive margin for anticipation of weak buses, or areas, and as well as the tangent vector, it can be implemented using the continuation method. It states the relationship of the steady state of the reactive power and the voltage magnitude as shown as in the image, and usually a positive value of the RPM can signal dynamic instability. As we can see in our graph, this region is a negative region of the QDQ, where we analyze the difference, and usually in the positive value of the positive region of the QB curve is where we can have our instability region of our system. Continuing with our route, the methodology that we use, as stated in the title of our work, we're going to be using the IEEE 57 bus system. Our calculation of power flow were carried out in MATLAB, and the method that we used was the Newton method RAPS. First, we're going to have an initial base case scenario with any renewable sources, basically the IEEE system as it is. Later on, after calculating some information from the base case, we're going to be selecting some buses to inject the renewable sources. Each renewable source will be removed then individually, just to analyze the impact of this. The renewable sources, something that we need to point out, the renewable sources are modeled as active power injections equal in magnitude to the active power demand of each bus. In other words, if we have a bus that has a load of 10 megawatts, our injection in renewable source is going to be as the same value of this load. In this case, a 10 megawatts load is going to be 100% injection for this case. And as well, something that we need to point out is that this analysis is going to be as snapshots. We're not going to carry out a dynamic analysis. It's just going to be snapshots because we're going to be analyzing some specific points of our day. In this case, our snapshot is going to be carried out as every single renewable sources in 100% scenario. First of all, the base case with no renewable sources, the tangent vector calculates the bus 31 as the critical bus of the system. For the LBS, we try to calculate most of the LBS values. Only 16 values managed to convert. The rest of them, they were diverging in our calculations. For the RPM, you can calculate every single bus, but for practical reasons, we're going to only analyze the values in which the LBS converges. For the no renewable sources, this is our ranking with the first 10 values calculated. If you can see the tangent vector, energy function, and the reactive power margin, the most critical bus for every single one of them is the bus 31. In the TV, what it means is that the bus 31 is the critical bus, but for the energy function and the RPM, this bus, what it means is that it's the bus with the lowest robustness of the system. And if you can see the rest of the ranking, they differ from the position in every single one of them. Even some buses, they don't even appear in this ranking because the robustness and criticality are two different information from these DSIs. As stated before, we use the partitioning parameter just to calculate the system critical area. I'm not going to talk about too much about this because we're going to take too much time. But what we're using here is just to calculate the neighboring buses in relation with the critical bus to determine in which region we have our critical actuation area. We determine a parameter under 0.6 as a stopping parameter, and we determine this area as a critical area without no renewable sources. Now we have these renewable injection scenarios. We as well calculate the tangent vector, which it provides us that the bus 31 is still the critical bus in our system. But with this information that we provided with the base case scenario, we managed to determine which buses we're going to have the injection of renewable scenario. The buses 19, 20, 42, and 56 and 57 are going to be selected. The buses 19 and 20, they fall out outside the critical area, appearing in the position 25 and 29 of the tangent vector ranking. This is important to notice because Our critical area, if we remember, this region basically englobes all of these buses, and we managed to put these three renewable sources in these buses, but these two, they're outside the area. So we managed to, we do it this way just to analyze the effect of having outside of the critical area some renewable injection, and what's going to happen if we have inside the critical area some renewable injection. For the first, we say the first scenario with renewable injection is going to be with 5 renewable sources. The VSIs are going to be calculated. If we can see, the reduction of the critical area is noticeable. We only have around 5 to 6 buses in this critical area, showing as well that, as stated before, the tangent vector showing the bus 31 as a critical bus in this case. In here we have the table where we show every single value, possible value of the energy function in comparison with the tangent vector and reactive power margin. As we can see, the tangent vector shows the same critical buses with the rest of the position differing from both scenarios. As well, the energy function and RPM yield similar and consistent ranking in both scenarios. Basically, they don't change too much. They change little position, and what they change is the value of their scalar value. But in case of the tangent vector, basically it changes most of the position in a greater way. Here we have a quick comparison of the critical area scenarios. The left is the no renewable injection, and here we have the 5 renewable injection scenario. You can see there's a noticeable reduction when we have the renewable injections, but as we were stating before, we're going to be removing one by one our renewable sources. You can see in the left we have our 4 renewable injections, our renewable injection in the left, and in the right we're going to have the 3 renewable injections. And you can see when we were taking one by one, the critical area is going to be increasing more and more. Here is the last analysis with 2 renewable injections on the left and 1 renewable injections on the right. And when we remove the last renewable injection, we're going to be again in the base case scenario with the big critical area. We have these visualizations of the heat maps so we can analyze the robustness of our system. The left graphs show us the distribution of energy function, and the right image is going to show the RPM distribution. As you can see, basically they provide same information, almost the same information. The critical, the more robust area are going to be shown in both VSIs. Basically, it's showing, providing that these two methods provide similar information for our system. And now we have, with heat map visualization, we have these 5 renewable injections scenarios. As you can see, as before, most of the information that we have of robustness is almost the same in both scenarios, with 5 renewable sources and with no renewable sources. Just to state the conclusions in future work for this presentation and ending our route, the combined use of VSIs offers a complementary and comprehensive assessment than any indicator in isolation. Basically, the tangent vector provides us a global view on the critical path toward voltage collapse, and it quickly identifies the critical buses of our system. And on contrary, the energy function and the RPM, it consistently features the local weaknesses of vulnerabilities and robustness of our system, the system conditions. The renewable injections, they alter in a greater way the criticality and vulnerability of our system. It reduces in a greater way the critical area, and it provides a robustness, a better robustness in most of the buses. And local renewable sources appropriately can contribute positively to the system stability by reducing stress on buses across the system. As well as stated before, the heat map visualization confirms these changes, providing a better perspective, a visual perspective of the robustness evolution as renewable penetration increases. While the tangent vector can identify voltage collapse trends, the energy function and RPM, it allows the operator to anticipate weak spots and local margins where reactive power support may be acquired. For future research on this work, we can extend to a larger network. We can incorporate as well dynamic aspects. We can consider the renewable intermittency and evaluating partial penetration in scenarios with the goal of supporting planning and real-time voltage stability monitoring in renewable based grids. We have, I can say that, thank you to the CEPOC 2025 Congress to the opportunity of sharing my work, as well as the Universidad Federal de Itajuba for providing me the knowledge and skills for this work, and as well to the OEA and CAPES for selecting me for the scholarship of my master's degree in electrical engineering at Unifaid. If you have any questions, you can, here's my contact information in Professor Elian Valenza and Antonio Zambroni. If you have any question, we can talk about further on this. Thank you for your time.